Okay. Okay, as I said, it would be really helpful to have an analytical relationship for the probability functions. And these are usually called probability distribution functions. And given that they are two, they are called cumulative probability distribution function or density distribution function. Okay, so it's probability density function and cumulative probability. But let me think, because there are many different terminologies, but usually they are called probability density function for the density, and it's the acronym that is used is PDF. PDF. And also they are called CDF. It is called CDF, the cumulative distribution function. So probability is dropped usually, but to be rigorous, it would be probability distribution function. This is fine, and cumulative probability distribution function. This would be the rigorous definition. But usually these two acronyms are used, and some textbooks use capital letters for the CDF to make it clear the difference. And usually, as I already mentioned to you, it's lowercase p for the probability density and capital P for the cumulative density. Okay. Now, I am just opening the slides because I want to make sure that I use the same symbol that are used in my slides. Just 1 second. Now, the literature proposed many possible analytical relationships for explaining these two curves, for describing these two curves. And the reason why they proposed many of them is that, as I said, the analytical relationship must provide a correct interpretation of what you would find empirically. This means that the analytical relationship should adapt to the data, to the behavior of the data, to the probability of the data. And therefore, this means, just 1 second, because I want to make sure that I use the same symbols, so I need, okay, that's fine. Okay. So they have to provide, as I said, a good interpretation of the probability of the data, which means that unique analytical relationship doesn't fit all. So the literature provides many analytical relationships. For instance, I give you a very simple explanation for the need to have many different analytical relationships. There are some random variables that are positively defined, like the river flow, others that are defined in -infinity plus infinity. So it means that when you define a general probability Px, or capital Px, where x is a generic random variable, if x is defined in -infinity plus infinity, or it's defined from 0 to plus infinity, of course the shape of the analytical relationship is different. And there are many other reasons to justify the need for several analytical relationships. And one other reason to one other solution to minimize the number of different analytical relationships is to use parametric functions, is to use parameters in these analytical relationships. Because you already know that parameters, I define parameters for rainfall of models. The meaning of a parameter is that it's a constant which changes the shape of an analytical relationship, but not its structure. So if you introduce a parameter, you can, using the same analytical relationship, get different shapes. So given that flexibility is needed in this case to describe these curves, people thought at the beginning to use parametric functions. And then they realized that they needed more than one parametric function. So the literature proposes several different distributions. And of course, the choice of the distribution depends on the physical behavior of the random variable. So if you have river flows, for instance, you may select a different probability distribution with respect to rainfall. And how to make the choice? Very often the choice is a trial and error procedure. You try with a given analytical relationship and you see if you get a good fit. And how to assess the goodness of the fit, I will explain you later. And of course, in order to make this choice, this trial and error choice, trial and error selection, you need to know what probability distribution you have available. And of course, you don't need to know all of them, but you need to know some of them in hydrology. And therefore, I am introducing now some analytical relationship. I also look at the slides because I don't remember them by memory, and you don't have to remember them by memory. But you have to know that they exist and what are their behaviors. And the first one that I introduced, which you already know, I am sure, it's the Gaussian distribution or normal distribution. It is not very useful in hydrology, but still it's very important. So let me start with this distribution. In my slides, you will find everything I mentioned today. So I didn't use them because I wanted to use the blackboard. And you know, when I'm using the blackboard much, I don't want to have the screen displayed because otherwise it's distracting. But you will find everything, not as detailed as I did, but you will see that you have support. And especially for this part that I am starting now, probability distribution function on the slides, you have everything. So, first of all, as I said, Gaussian distribution or normal distribution, they are synonyms. Gaussian derives from the name of Gauss, a famous statistician that lived, I don't know, I would say 1700, 1800 more or less. And it's also called normal. I will tell you later why it's called normal, and it's very important to notice. So let me provide now the relationship. You already know that it's we could express the analytical relationship for the PDF or the CDF. It doesn't make any difference. In this case, because you can pass from one to the other by using an integral. In this case, I provide to you the relationship for the PDF, and in my slides it's also I'm using the symbol F. You will find very often the symbol F and the capital F for lowercase p, capital P. Sorry for this, there is inconsistency with my slides, but don't be too much linked to the symbols. You have to be flexible. And basically it's written in this way: 1 over the square root of 2 pi sigma square and E minus, I always try to learn it by memory, but then I get convinced that it's not so useful. And so this is a 2. So it's 1 divided by the square root of 2 pi, this is pi sigma square, and sigma is a parameter, and we'll introduce the parameter now, multiplied by e to the power of minus x, x is the given value of the random variable, minus me is another parameter, squared divided by 2 sigma squared. So two parameters, mean, me, and sigma. So what are these two parameters? Me is the mean of the random variable, or mean of the distribution, let's say mean of the distribution, which of course should be coincident with the mean of the random variable if the distribution is fitting the random variable well. And then sigma is the standard deviation of the distribution. So I think it's clear for you what is the mean. I'm not sure it is clear what is the standard deviation. So let me introduce both of them. And let me define both of them. But I'm not defining them in a rigorous way. I'm just giving to you the relationship for the estimator of the mean and standard deviation. Estimator means that you have a series of outcomes, and then, basing on the series of outcomes, you estimate the mean and the standard deviation. It's different with respect to estimating the mean and the standard deviation of the random variable, because the random variable is like the underlying principle. The outcomes are the results of the experiment. So if you estimate the mean on the outcomes, of course, if you have many and many outcomes, this is very close to the mean of the random variable. But they are not the same. The random variable, as I said, is like the underlying principle. Like tossing a coin. Okay, tossing a coin, the result is your random variable. If you don't know anything of tossing a coin, let's suppose that you want to estimate, not the mean, because this is a binary variable, but let's suppose that you want to estimate the probability of getting a net. So you could make the experiment. But let's suppose that you make just one experiment, one toss. Then you can't estimate anything. Estimator, empirical estimator, means that you estimate based on the outcome of the experiment, and you try to estimate the underlying principle, which is the probability of getting the net. So basically, in this case, you have a random variable, you have several outcomes, like observation of river flows, and you want to estimate the mean. So if you have several outcomes, you just compute the mean, and this is your estimate, and it's close to the mean of the random variable. But let's suppose that you have just one observation, or two. Then your empirical estimator gives to you a number, which is not very reliable. But still, the empirical estimator is very useful to understand what is the mean and what is the standard deviation. So I am using the empirical estimator to define them, which is not rigorous. So the mean is very simple. If you have n observations, then, and you denote each observation as xi, the mean is given by 1 over n, and capital N is the number of observations, multiplied by the summation for I equal 1 to n of the xi. This is the mean. Do you have a question?
Can you show it in the diagram that you already drew?
Which diagram?
You draw the diagram of the P.
Okay, so
I'm talking about the mean, to show the mean distribution of
yeah, okay. I think I understood your question. Just 1 second. So you want a diagram with x and here lowercase px for the Gaussian distribution, correct? Okay, that's fine. So let's suppose that the mean is 0 of the distribution. First of all, I am anticipating what I would have said. So now I just suspended this part here. You have to define the standard deviation. I will do it in 1 minute. But let me reply to the question. So first of all, this distribution is symmetric. Symmetric means that it's defined between minus infinity x plus infinity. So if you look at this analytical relationship, it's defined between minus infinity and plus infinity, and it's symmetric with respect to the y-axis, to the ordinates, which means that you get the same value if you get minus x and plus x. And you see this because it's squared. So basically, it's, let me say, it's, no, it's not just because it's squared. But if you look at the relationship and you try to change x with minus x, you get the same result. And it is like so. Should be symmetric, so if it doesn't look symmetric, then it's a mistake. And then here I am stopping, but it should asymptotically should converge to 0. And the reason why I am stopping here is that this distribution is quite concentrated around the mean. The Gaussian doesn't allow you to describe variables, random variables, which occasionally take very high values or very low values. The Gaussian is fine if all the values are quite compressed around the mean. Tomorrow I will show you some realization, meaning some outcomes from the Gaussian distribution. You will see that it's very unlikely that you get values that are very far from the mean, and the mean is here. Now, the standard deviation. The standard deviation can be estimated in this way. If you have the same series of xi for a total number of capital N, then the estimate is 1 divided by n minus 1, which multiplies the square root of, the square root is here, and which multiplies the summation of xi, summation from I equal 1 to n of xi minus me squared. This is the estimate of the standard deviation. What is the standard deviation? It's an estimate of the variability. The mean provides an indication of the central tendency. Central tendency, it's an intuitive quantity. The average means the value that is more likely for the distribution, the central tendency. The standard deviation is an estimate of the variability. Look, these statistics, which may look arid or meaningless, from a physical point of view are extremely important. If you deal with a series of river flows, the mean value is extremely important to understand what the river looks like. So if I say that the mean value of the river flow of the Po River is 1500 cubic meters per second, this is a very important information for water resources management. And also the standard deviation, the variability. If you see that a river flow series has a low variability, you are very happy, because it means that your water resources availability is quite constant over time. Instead, if you have a huge variability, this is concerning, because it means that you may experience very huge floods and very severe droughts. If I could say, look, the average of the river flow of the Po River is 1500, and the standard deviation is 0, this means that any time you would have an availability of water resources which is equal to 1500, which is perfect, because you design your water supply systems on this water resources availability. Instead, if you have a series that is variable, huge variability, what would be then the design variable for water resources supply system, for your water supply system? You know, because if you take as design variable the mean, then when you have higher flows, your water supply system cannot take advantage of the higher flows. And on the other hand, when you have low flows, then you don't have enough water. So variability is extremely important. This standard deviation, which looks like a meaningless number, it's extremely important. And there is another statistic that is extremely important, which I will introduce later. But anyway, these are the two parameters of the distribution. And of course, if you look at the graph here you can see that me is equal to 0. If you change me, you can shift this curve along x. And where do you see the standard deviation here? The standard deviation is given by the width of this bell. Keep in mind that this is a probability density, so the integral between minus infinity and plus infinity is 1. The area here, this area is 1. So, if you increase the standard deviation, you get another shape that looks like this, for instance. If you increase the standard deviation, you increase the width of this bell, and therefore the top gets lower down because the area beneath the curve, under the curve, is always 1. Okay, this is the first distribution. Why it is so important? First of all, let me say that given that it's defined between minus infinity and plus infinity, and given that it's then defined also for negative values, it's not very useful in hydrology. So one may say, why did you introduce it to us? And the reply is the reply to the question why it's important is simple but extremely meaningful. The Gaussian distribution, it's called normal distribution because when you have a random variable that is defined over time, like river flows, random variable that depends on time, you may substitute the random variable with its aggregation over time. So let me explain in more understandable terms. River flow, observed at hourly time scale, you could substitute it with the daily time scale. You aggregate, and usually you take the average to do that. And then you can pass to the monthly time scale. You take the monthly average. This is another aggregation. And then you can pass to the annual time scale. Depending also on the purpose of your analysis, you may aggregate the random variable over time. Now, there is a theorem in statistics which is called the central limit theorem. Which says, and we don't prove it, which says that for increasing aggregation over time, any random variable, depending on time, converges to the Gaussian distribution. Again, for increasing aggregation over time, any random variable, depending on time, converges to the Gaussian distribution. And this is why it's called normal. This is amazing. If you think at it, it's amazing. So you could have random variable, river flow, rainfall, number of potatoes, number of tomatoes, whatever. If you increase the aggregation over time, you converge to the Gaussian distribution. You could try. Take, for instance, I can give you a time series of the river flow of the Po River. You could try, it's daily, you increase the aggregation, and then you get very close to the Gaussian distribution. And this means that in randomness there are rules, which of course it's, it's understandable because tossing a coin is a completely random process, but there is a strong rule. The number of heads is equal to the number of tails, on average. Another rule, which is less intuitive, is this one. Again, for increasing aggregation, any random variable expressed as a function of time converges to the Gaussian distribution. It's not necessary that the random variable is expressed as a function of time. It could be also expressed as a function of space. Increasing the aggregation brings any random variable to the normal distribution. This is extremely important and nice also. But still, in hydrology, we can't aggregate much, usually. We are not interested in the annual time scale. We usually are interested in the hourly time scale, daily time scale, and therefore, the Gaussian distribution is not very useful for us. So, and also, there is this fact that our variables are positive in most of the cases. And what is a consequence of the fact that they are positive plus the physical behavior of our variables? Let's think at the river flow. The consequence, and I'm going to prove it, is that the probability distribution is not symmetric. Why that? Another thing that I forgot to say is that this normal distribution, I gave to you the expression of the density, the integral, the function cannot be integrated analytically. So this is why I gave to you the density and not the cumulative distribution. And this is something that is really, how to say, it's not healthy. If it were analytically, if the integral could be computed analytically, it would be much better for us. Unfortunately, it cannot, and therefore this is a blame that we should address to nature. She should have devised a limiting distribution that is analytically, can be handled analytically. This didn't happen. Okay, there are philosophical explanations for this. And the philosophical explanation is that nature cannot be very simple, because if it was simple, it would be defeated by the enemies. So basically, there is also a philosophical interpretation that say that nature should be unpredictable, because any time that we are predictable, we are vulnerable. Think at the people that try to escape from the danger to be killed. They change every day the road that they follow with the car. They change every day their behavior because they want to be unpredictable. And therefore, there is a philosophical interpretation, not descending from this, but in general, a philosophical interpretation that says that every living species, every living system should be unpredictable to maximize the probability to survive. And this is also why sometimes the animals like wolves or foxes, they behave in an unpredictable manner, because being unpredictable, they survive. And there is an interpretation that even nature has to be unpredictable, because otherwise, think about floods, for instance. If they were predictable, then the living entities could avoid them. And if you avoid to get trapped by a natural hazard, then the natural evolution is not taking place, because extreme situations are a way for nature to make natural selection, and for living species to experience natural selection. So the philosophical interpretation is that if nature was predictable, then living species would get extinguished, because they couldn't experience the natural selection. This is philosophy. Let me say that in any case, has nothing to do for now with our, but there is, in hydrology, there are some researchers who say that this is why floods are unpredictable, because otherwise, you know. Okay. So let me go back to our original problem. The original problem is that we have to, this fact that the variables are asymmetric. So why that? Let me consider river flows then. Here you have Q, and it's defined from 0 to plus infinity. And here you have the probability density, PQ. First of all, it cannot be lower than 0. So you start from here, and if you take whatever observation of river flows, especially at fine time scale, like hourly, you see that the average is close to 0. The maximum value is very high. So let me make an example, for instance, for one river which I know well, which is an Apennine river, the Secchia River. The average is about 16 cubic meters per second, and the maximum value is about 1,000 cubic meters per second. So 16 is very close to 0, 1,000 is very high. So basically the probability test that you get is something like this, which is highly asymmetrical. And then you may ask me, this is me, you may ask me, how can I get close to Gaussian with such a distribution? Very simple, because when you take the average, if this is hourly data, when you take the average to daily data, the maximum that gets decreased. Because the floods last for 3-4 hours, and then if you take the average over one day, the floods get decreased. If you get the monthly average, then the maximum for increasing aggregation gets closer to the average, and the distribution gets closer to symmetric. But if you deal with data that are observed at fine time scale, then you get an asymmetric distribution. So the Gaussian, again, is not fine. So what is a possible solution? There is a very simple possible solution, which is the log normal distribution. What does it mean, log normal? It means that you get logarithm over base e, or over base 10, it doesn't change much. You take the logarithm of your river flows, and then the logarithm can be modeled with the normal distribution. Of course, the log normal distribution is asymmetric. Think at the logarithm or the exponential function. If you start from a symmetric variable, then if you take the exponential of the symmetric variable, the highest values of the variable get stretched a lot, while the low value, more or less, they are not changed much. But the higher values are stretched. So the tail of the distribution, this is called tail, when you take the exponential, is stretched. And in fact, the normal distribution is much used in hydrology. And also it allows you to eliminate the negative values. The negative values become values that are comprised, included in the range 0, 1. So it's a positive distribution, positively defined, asymmetric, it's fine. And the parameters are still two parameters, like the normal distribution. Because it's nothing else than a normal distribution applied over the logarithm. Let me see if I am forgetting something. Just 1 second. Okay, yeah.
Excuse me, Professor, could you repeat why the Gaussian distribution, that one, is not fine for which kind of data?
Yes, it's symmetric, and therefore it's not fine for the negative, for data that are positively defined, and also, which is more important, it's not fine for data that are observed at very short time scale. For increasing time scale, it becomes fine. Let me define a last distribution, and then we are ready to move forward next time, which is, again, quite important, even if it's very trivial. And this distribution is the uniform distribution. Okay, so the uniform distribution, first of all, is defined in the interval between A and B. So A less or equal than X less or equal than B. So let's plot it. I indicate A and B, A in the origin and B here. Or let me say, just to make it more general, let me A here. And the uniform distribution in terms of density, is like this. It gives equal probability to any value between A and B. And of course the area is 1, and therefore the probability, let me call it just lowercase p without any dependence on x because it's constant, p is equal to 1 divided by b minus a. And probability is equal to 0 for x lower than a and x greater than b. This is